We begin looking at the characteristics of functions by trying to answer two essential questions. What makes a relation a function, and how do you determine and describe the domain and the range of a function? You might even be able to answer some of these questions already or identify some of what these words mean, but let's look into it a little bit further. When we first see relations and functions, we see this mapping sort of scenario where we have things written in ovals typically, and we see something like A maps to 1 and B maps to 2, maybe C maps to 4, D maps to 3, as an explanation of what a relation is. And it's simply just taking something we might call input here and output here, and it relates, the word relation, it relates the A to the 1, the B to the 2, the C to the 4, and the D to the 3. That's an example of the definition of a relation between two sets. You might see something like H relates with 3, maybe R goes with 7, and maybe R also goes with 9, and Z goes with 6 is an example of a relation between this first set and the second set. Notice that the number of letters in the first set here is less than the number of numbers in the second set. That's okay too. Here's another example where all the inputs all sort of relate with the same output. All of the items in the first set give you an output that's the exact same, no matter what the input is. Now those are all examples of relations, so what makes one particular relation a function or not? A function is a special kind of relation. Well, in a function is a special kind of relation. That's an E. A function is a relation where each input has no more than one output. So with that definition in mind, a function is a relation where for each input, that input has no more than one output. For instance, this first example here is an example of a function because each input, A, B, C, and D, are mapped to or relate with just one particular output. So the A maps with 1, B with 2, C with 4, and D with 3. But in the second example, this is not a function. Because, can you see which input relates with more than one output? It's the R. This is the reason why this is not a function. R has two outputs. It has an output of 7 and an output of 9. What about this last example? For each input, does each input have no more than one output? It looks a little bit different than the other ones, but this is a function. And a lot of times we see this idea show up to give you an idea of what a function is with this function machine. You might see this in middle school where you give the function machine an input like A. The function machine does something on the inside and spits out an output maybe like 1. So we don't necessarily know how, but the function takes an input, gives you an output, and that's what we see happening there. Now, graphically speaking, we have the vertical line test, something that you've probably seen before as a way to determine if a graph is the graph of a function or not. Now, a vertical line test says if you can pass a vertical line through the graph so that it touches the graph at more than one spot at a time, and here obviously this vertical line crosses through this circle or oval more than once, this is not a function. If you can see this first graph, this diagonal graph, this is a function. There's no vertical line that we could draw. And we can, a trick is to maybe hold up your pencil or take something really thin and hold it vertically and pass it across the entire graph. You can draw a vertical line here and here and here and here. There's nowhere on that graph where the vertical line will cross more than once. This zigzag kind of graph, we can pick a spot so that it crosses actually 3 times. All that it takes is one vertical line to pass more than one point on the graph for the relation to not be a function. Now these are all relations. We can pick points on any of these graphs and come up with what we would call an x and a y coordinate, which is the definition of a relation. It's just not a particular kind of relation called a function. Now what about this last one? Kind of looks like an upside down U, downward facing U. If you think about vertical lines that go through here, this is going to be a function because it passes the vertical line test. So that's the vertical line test graphically tells us whether a relation is a function or not. Sometimes a mapping gives us an idea of a relation or not. This mapping from x to y we can kind of call this set x and maybe this set y. We can go back and call this x and this y, this x and this y. So you see this input and x go together, output and y go together. That's going to be important here in just a minute. Once we start talking about functions specifically, we can take things like equations that we're used to seeing in y equals, let's say, negative x squared plus x minus 2. We start seeing equations that are written like this, written in function form. Now function notation will change the y into f of x. And so instead of y and x, we have this f of x notation, and it's going to be the same thing as y. It means the same thing. And we use it interchangeably with y. And so now you've got this equation written in function notation. And one of the reasons why that's nice is with function notation, we can write something like this and communicate that we want the input right here, we want 1 to be the input into the function f. Well, we've defined the function f above, and so in the place of x, we're going to put 1s. Everywhere there's an x, we'll put a 1. And then we'll be able to sort of do the multiplying, do the adding, do the subtracting, and get an answer for what the y value is equal to when x is 1, and call it f of 1. So 1 squared we're going to do first, that's 1. Take the opposite of it, it's negative 1 plus 1 is 0, so this answer is going to equal negative 2. And we can write that as f of 1 equals negative 2. We know our input, our x, is right there. We know our output, our y, is right there. So that's one thing that's nice about function notation, is it includes all in one equality statement, both the x and the y. If we did something like f of negative 1, what does that equal? See if you can figure that out with me here. It's going to be the opposite of negative 1 squared plus negative 1. We're plugging in negative 1 for each of the x's. Minus 2. Do some squaring, that becomes a positive 1, negative 1, negative 2, and we should end up with negative 4. So f of negative 1 equals negative 4. And that's an example of function notation. We saw earlier in the video this idea of input, and we called it also this x. Well, in function notation, when we're talking about functions, we typically refer to the input, and usually that's the x values. It's not always x, sometimes maybe t for time, but typically x values. That's the domain. And we usually use a capital D to show the domain. And the output values, which we also kind of called y, are the range. And those are the y values, or the function values. If we're going to stick with function notation, those are the function values. Instead of using y, we can talk about function values, and that's a capital R is the range. I'm going to look at a few examples of graphs and trying to determine the domain and the range of the graphs that we see, even not necessarily knowing what the function is. We're going to draw a graph and see if we can't figure it out. So let's plot a few points. This is the point 3, -3, and we'll plot a few points here next to it, here next to it, if I can get my pen to work. Here's a point up here, here's another point up here, and we're going to draw, this is starting to look like maybe a graph you recognize from last unit on parabolas, and here's something that looks parabolic. Now, what is the domain and what is the range? So the domain, we're going to use the letter D, and we're going to describe the domain. Now, what x values, the domain, the input values, what x values, here's your x-axis right here, what x values are included in this graph? Well, is the x value of 3 included on the graph? Sure, right here there's a point that has an x value of 3, right? Is the x value of 4? It's right here. What about all the values in between 3 and 4? How about 3.2 maybe? Sure, there's a point over here. 3.5, there's a point. There are points everywhere between 3 and 4 x values. There are points actually on the curve. What about x equals 5? There's a point right here. What about x equals 1? There's a point right here. All these x values have corresponding points on the graph. What about x equals 6? The way I drew the graph, it looks like maybe up here there might be a point at x equals 6, but what about x equals 7? That's off the edge of the graph. Well, we have to use our imagination and trust that if we could see more of the graph that we actually can see, it's going to continue kind of up in further to the right in that general direction, and we're going to be able to sort of make the assumption or use our imagination to assume both sort of towards the right here and also sort of towards the left there, that this graph is going to keep going up and keep going left and keep going right. And in that way, we're going to be able to say that the domain, every x, every positive x, every negative x, this graph will eventually have somewhere, maybe really, really high off the edge of the screen, it's going to have a point on the graph for that x value. And so when we do that, we say x is starting from -infinity all the way to +infinity are included in our domain. All of those numbers, that represents all real numbers. Sometimes we use a symbol that looks like a capital R with 2 vertical lines to represent all the real numbers for x. If we now take that same approach but talk about the y values for this graph, what y values or values in our range are there? Is there a y value of -3? Well, sure, that's the vertex right here has a y value of -3. Is there a y value of -2? Well, this point right here, and actually this point right here also has a y value of -2. How about all the y values in between? Are they there? Yes, they're there. But what about below -3? What about -4? Are there any points on this graph that have a y value of -4? And the answer is no. And you can see, therefore, that our range actually starts at -3, and there's a point with a y value of -3, so we're going to include that in our domain or in our range. And all the y values that are actually above -3, so that's heading in the positive direction. And if this graph does continue, if we use our imagination for this graph continuing up forever, that range, the y values will eventually include all the positive y values all the way to infinity. Well, let's look at another example, another graph, and see if we can't come up with the domain and the range for that. Let's put a point maybe right here, if I can get it. There it is. And that looks to me like the point -5, 3. And let's do something like this kind of a graph. Okay, and let's analyze if this is sort of where the graph starts, that -5, 3, if that's where the graph starts, what is its domain and its range? Well, let's do the same type of analysis. The domain, D, what x values on our x-axis can we see show up on our graph? Well, how about -5? Is it there? Yes, it's there. How about -4 right here? How about -3 right here? How about -6? No, there's nothing. In fact, there's nothing between -5 and -6. So this domain starts at -5, and is it going to keep going to the right forever? we use our imagination and we see that this graph will probably keep going right forever, so we say its domain, the x values are all the positives that are included after we sort of beyond what we can see off the edge of the screen. Well, what about the range? This range is a little bit different because this graph goes downward. It actually has a point, and we've identified the y value here of 3. That's actually the highest point of the graph. And all the y values down here we can pick are covered by this graph. And so this range actually starts down at negative infinity and stops at positive 3. That's the last y value sort of on this graph. None of the y values go any higher than that. Two more quick examples and that'll be it for today. A graph that might look something like this, we could analyze for its domain and range just like we have with the previous examples and see that the domain is all real numbers. Every x on the x-axis has a point on that graph. We can find a point on the graph with that x coordinate. And the range is also all real numbers. Every y is covered somewhere up by this graph. Sometimes some y's more than one location, this point and this point, but all the y's from negative infinity to positive infinity are covered. Now there are some special graphs that look like this last one. It's going to, the best way I can describe this is start really, really close to the y-axis and it bends and it gets really, really close to the x-axis, but it doesn't actually ever touch. And then down here, the same situation where it gets really, really close below the x-axis and really, really close to the left of the y-axis. And when we analyze that for domain and range, we see something like the actual x value of 0, there is no point where the x value is 0. So it's like everything but 0, which we know how to write in interval notation like this. This shows us all the x values from negative infinity to infinity, but not 0. And similarly, the range doesn't have a y value of 0 because the graph is just getting really, really close to the x-axis over here, but not touching it, and really, really close to the x-axis here and not touching it. And so this range looks a lot like the domain, and it's all the y values but 0. So here are some examples and some ways to figure out the domain and range of functions, and that's it for today.